Okay, today we're looking at section 7.3, functions involving E. E is the Euler number. Some people pronounce it Euler. Could be Euler or Euler. But it was discovered by a mathematician by the name of Euler. I believe first name Leonard. The number comes from taking this expression here, 1 plus 1 over n to the n power, and as you increase n, the number approaches a specific number. So if the bigger number I plug in, it keeps getting closer and closer to the Euler number, which is this number right here, which we can round to 2.72. On your calculator, you can find that number. On this calculator, the TI-84, it looks like it's above the division sign, so I have to hit second division sign, and there it is, the Euler number right there. If I hit enter, I get the actual numerical value of 2.72. Okay, so it's similar to like any other number like pi. It's just a mathematical number, and it's used in different mathematical and scientific situations. It's also used as a base often in exponential growth and decay problems. So the general form will look like this: AE to the RT. R is my rate, A is my initial amount. If R is greater than 0, then we have exponential growth. If R is less than 0, we have exponential decay. So that's what we're looking at in this situation to determine whether we have growth or decay. Okay. Graphing, very similar to what we were graphing before. Here's our general equation. Here's my rate. We may have a horizontal shift or a vertical shift. The K is still the asymptote. Only difference here is we probably will have to rely on our calculator in order to make the table. So let's just do a quick simple graph here. 2e to the 0.5x plus 1. So this is going to be exponential growth because 0.5 is a number that's greater than 0. Okay, I'm going to draw the horizontal asymptote. And then I'm going to plug in -1, 0, and 1. Again, I'm plugging 0 in because that makes the exponent 0. It's an easy number to plug in. Okay, so again, you make your table the same way as we did the other ones. So I can plug in 0 without a calculator because if my exponent becomes 0, e to the 0 is 1, times 2 is 2, plus 1 is 3. Okay, these values are going to end up being decimal, I believe. So let's just plug in -1. 0.5 to the -1 is -0.5. So I'm going to go e to the -0.5. See what I get there. Whoops. E to the -0.5. Multiply that answer by 2. And then add 1. I get 2.21. Okay, let's plug in 1. 0.5 times 1 is 0.5, so let's go e to the 0.5. I get 1.64 times 2, 3.29 plus 1, 4.29, so 4.3 actually. Got my three values. Let's see what I get. -1 is 2.21. Zero is 3, and 1 is 4.3. So you can see what's happening here. We know this is exponential growth. This graph is looking like this. Okay. So we graph it the same way. The only problem is the base is inconvenient, so we use our graphing calculator to help us out there. Okay. Domain and range. Domain, all x again. Range, y is greater than 1. That's my asymptote there. Okay. So let's look at one quick application of E. is the formula for continuously compounded interest. Okay, that's different than compounded daily. This is continuously compounded. Okay, here's the formula, PE to the RT. So it's a fairly easy one to remember if you remember the word PERT. RT is the exponent. So P is my principal, E is just a number, R is my rate, T is my time. So here's the problem. $5,000, 6% compounded continuously. How much will I have in 5 years? 5,000 is my principal. E to the 6%, so that's 0.06, and the years is 5. Okay, so now the only thing that's going to hang me up here is if I don't follow the order of operations properly. Okay, so I'm going to clear this. I'm going to put this whole thing in at once. 5,000 E. Actually, over the natural log button is e to the power. So I'm going to go e to the 0.06 times 5. And I get 6749.29. So $6,749.29. So it's a real simple plug-in formula. We can just plug numbers in and get our answer there. Okay, the other thing that's in this section is simplifying expressions with E. It's just a little review of simplifying with laws of exponents. So just here's a few examples we'll go through real fast. So when I have the same base, what do I do with the exponents? I add those exponents. So this is going to be e to the 4. Okay. This one looks a little tricky because I have variables in the exponent, but I can still add these and get one exponent. So x plus a negative 2x is a negative 1x plus 4. So that would be my answer there. I'm just adding the exponents. Okay. Power to a power, we have to multiply, right? This is 2 to the 1 to the negative 4 would be 2 to the negative 4. This would be e to the positive 8 multiplying. So then I can take and put e to the 8 in the numerator, 2 to the 4 in the denominator. If I want to go further, I can write it as e to the 8 over 2 to the 4th, which is 16. Okay. Next one. This one could be looks a little tricky. What I can do here, when I have division, what do I do with the exponents? I subtract them. So this is going to end up being 4e to the x minus 4x, which is negative 3x. Okay. And finally, the last one here. 6 divided by 2 is 3. This is going to be e to the what? This is e to the 1, so if I subtract these exponents, I get 4x minus 1. They're not common, or they're not like terms, so I have to just write it like that. Okay? All right. So that is it for section 7.3.